today we're going to look at titration. And titration problems are basically 4 problems in one. Okay, so you've just watched a video on the titration curve and identifying different points there. We are going to now learn how to construct a titration curve, and we have 4 main points that we want to use. So the first point is the initial concentration of your weak acid or your weak base. Okay, and I'm starting with example problem 8. Right, so your initial concentration of your weak acid or your weak base. Right, what is the pH at that point? And then we want to know what is the pH at the half equivalence point, and then at the equivalence point, and then we want a point beyond that equivalence point, so 10 to 20 milliliters after the equivalence point. Okay, so the first one, the initial concentration of the weak acid or weak base, is just the same kind of problems we've been doing, right? And so we have 0.1 molar acetic acid. Right, so we write our ice chart for acetic acid dissociating. We set up that ice chart. We have 0.1 molar. We don't have any of either of these. We have minus x plus x, and we get 0.1 minus x, and x. Right, and then we calculate our x. So we plug into our equilibrium expression. 1.8 times 10 minus 5 is equal to x squared, then over 0.1 minus x. Right, we use our solvers and we find our x. And then we find that x in this case is 0.00133 molar. And so then we can find the pH by taking the negative log of that. Right? And so we get a pH of 2.88. Alright, so that's the first point. Then our second point, right, is the pH at the half equivalence point. So the half equivalence point, as you learned in the previous video, is the point where the pH is equal to the pKa. So to calculate the pH at that point, it's quite simple, right? So we take the negative log of our Ka, which is 1.8 times 10 to the minus 5. And we find that it is 4.74. Now again, this makes sense, right? Because we're titrating, so we are adding a strong base to our weak acid, so we see our pH going up. Okay? Alright. So then the third point is our equivalence point, and this tends to be the most tricky point for calculating. Right, so what we have is our chart, our acid. We'll set up our acid reaction with our base. Okay, and in this instance, we have to determine, right, how much is remaining. What do we have present? So we have our water, and then we have our acetate ion. Okay. And so in this instance, we have 50 milliliters, right, of a 0.1 molar solution, right? And so if we want to, in this step, find our moles, okay, so we have, and actually we're going to use what's known as millimoles, just because it makes the math easier, right? So milliliters times molarity gives you millimoles. So we have 5 millimoles of our acetic acid. And then we're going to determine how many millimoles of our sodium hydroxide, right? So again, our concentrations of our acid and base are equal, so if we're at the equivalence point, then those moles are equal, right? That's the definition of our equivalence point. Okay? So we have 5 millimoles of both of those. Right? Again, our water never matters here, okay? And we have none of our conjugate base, right? And so then we're going to consume, right, our 5 millimoles. And then over here, we end up with getting our 5 millimoles, right? So we have no acid, no weak acid, no strong base left. What we have left over, though, are our 5 millimoles of our conjugate base. Now, we have to use this to help us determine what our concentration of hydroxide is, and then our pH. So this ends up being much like a salt problem we were doing previously, right? And so we have our conjugate base and water. Remember, this is an equilibrium situation, right? And in that instance, our water gives hydrogen to the acetic acid, and we're left then with hydroxide, right? We have 5 millimoles here. We need the concentration, right? So to get to this point, right, we added 50 milliliters of our acid, and since they're the same concentration, the same number of millimoles, we also ended up adding 50 milliliters of our base. So our total volume then is 100 milliliters. So if we divide millimoles by milliliters, then we will get our molarity. So 5 divided by 100, we get 0.05 is our concentration. So that is our initial concentration. Right. So again, we didn't have any of either of those, right? We consumed those. So now our equilibrium shifts to the right, okay? And then we get 0.05 minus x, and x. And in this instance, we have a Kb since we have our hydroxide, right? So our Kb, again, to find that, we do 10 to the minus 14 divided by our Ka, which is 1.8 times 10 to the minus 5. And so our Kb is 5.6 times 10 to the minus 10. Right? And then we plug that into our equilibrium expression. Right? And so in our equilibrium expression, we have our 5.6 times 10 to the minus 10, right, is equal to our x squared over 0.05 minus x. We put that into our solver and solve for x. And we get 5.29 times 10 to the minus 6. Right. Again, that's hydroxide. Right. If we refer back to our ice chart, right, that's our x is our hydroxide. And so if we take the negative log of 5.29 times 10 to the minus 6, then that gives us our POH. Right? Oops, sorry. Okay, so we get our POH. That's 5.28, and so then our pH, of course, is 14 minus that. We get 8.72. So at our equivalence point, then our pH is 8.72, which makes sense because we're adding a strong base, so our equivalence point is going to be more basic. And again, the reason for that is since all the acid and the base are consumed, right? We consumed all the weak acid and strong base. What was remaining was the conjugate base, which still produces some hydroxide. Right, so then the final step is a couple of milliliters past the equivalence point. So our equivalence point happened at 50 milliliters of our sodium hydroxide. So let's do 10 milliliters beyond. And I'm arbitrarily picking that. You can pick any amount. I wouldn't pick anything less than 10. Okay? And I wouldn't pick anything over 20. So we're doing 10 and 20. Right? So our equivalence point happened at 50 milliliters. So we're going to do this at 60 milliliters of NaOH. Okay? So again, we have our weak acid. It's going to react with our hydroxide, and it's going to form water and our acetate ion. Okay? And so we set up our ice chart. We started out with a 0.1 molar solution here, 50 milliliters, which was 5 millimoles. Right? And if I use 60 milliliters of my 0.1 molar NaOH, right, and that is 6 millimoles. Right, again, our water doesn't matter, and we have none of our conjugate base. And so what's limiting this time is our acid, so that's -5, -5, and +5. We have none of our acid left. Here we have 1 millimole of our base left, and over here we get 5 millimoles for our acetate ion. Now, in the previous step, we calculated what the concentration of that 5 millimoles was. It was 0.05, and we calculated what the amount of hydroxide would be formed from that, right? And then we found right here that was 5.2 times 10 to the minus 6. Well, what is the concentration of our hydroxide here, right? This is in a total volume of, this is 50 milliliters, remember, and then this is 60 milliliters. So this is a total of 110 milliliters. And so the concentration of the OH here is 9 times 10 to the minus 3 molar, which is far more concentrated than was what dissociated out of the conjugate base, right? And so past the equivalence point, we determine how much of the strong base is remaining, and we use that to then find our POH. Okay? And then we can find our pH from there. So our pOH here is 2.04, and then we do 14 minus that, and we get 11.96. Okay? So from all of that, then we can sketch a titration curve, right? So we have our volume of titrant. In this case, that's NaOH, right? And then we have our pH, right? So at a 0 volume, right? We knew it was our initial weak acid pH, right? So 1, 2, 4, 6, 8, 10, 12, 14. I'll do 2, 4, 6, 8, 10. And again, this is just a sketch, okay? And so at 0, we found that at 0 titrant, we found that we were at 2.8, so we would plot that point there. Our half equivalence point, right? So our equivalence point happened at 50 milliliters, right? So 50 milliliters. So half equivalence point is half of that. So that would be 25 milliliters, right? And so at 25 milliliters, or half equivalence point, we saw that it was 4.74. So we'll plot that point. And then our equivalence point of 50 milliliters, we had 8.72. So we'll plot that point, right? And then beyond, we did 10 milliliters beyond. So I'll try to make it a little bit to scale here. At 60 milliliters, we did 11.96. So here. Now, this looks as though, right, it would just kind of be a curve like this. Remember, it's a titration, so it's got this S curve. Remember, the equivalence point is halfway through that steep point, right? So I draw the steep point first, and then I curve it back, right? This is not a very good curve, but I curve it back, right? So it's got to have that S shape to it, okay? And again, your equivalence point should be the middle, right? Your equivalence point should be in the middle. And your half equivalence point is in this flat region where we don't see very much change at all, and that's because that's the buffering region, right? Where we have a buffer because we have some of both our acid and our base present. Okay, so we're going to be working on this and problems like this for the next couple of days, and we'll be doing more of the problems in your notes in bell work. Okay, so if you want to try to do the problem on page 20 based on what we did here, you certainly can, but we'll be looking at that in class as well.